Sounds good, thank you. Yeah, so I'm excited to share some results about the improving multi-arm bandits problem. This is joint work with my advisor, Avrim Blum at TTIC. So let's first motivate this problem. Maybe there's some resource that you're searching for and you know it's in one of K locations and you want to try to find it as effectively as possible. Maybe slightly more relevantly to those of us in this room, we're training learning algorithms and they improve at different rates and they have different final training accuracies. And you want to decide which learning algorithm should get training resources. Or maybe you're like me and you've worked a little bit on this and a little bit on that and you're wondering which research direction has the best payoff. So we formalized this as a K-armed bandit problem. In this problem, we have each bandit arm has associated with it a function fi that is increasing as a function of the number of times it's been pulled. And so the interaction is as you would expect for a bandit problem. You pull the arm and you receive the reward. Our goal is to maximize the total reward. In the paper, we also talk about the objective function of the maximum reward ever received. But for the purposes of the talk, I'll just focus on this objective. And we're going to measure this by competitive ratio opt over alg. And the reason for this is because it's pretty easy to see that, or it's pretty easy to show that this problem has at least O of t linear regret. And so you get a better understanding of the problem in the competitive ratio. And past work showed that deterministic algorithms have an O of k upper and lower bound. And so we're going to extend to the randomized algorithm case. So following past work, we're also going to assume this diminishing returns property. And so what this says is that the value of the function changes by less as time goes on. And so this is a discrete analog to concavity. And so here's an example of a function that is not a diminishing returns function. This is also a function that is not a diminishing returns function. But this one and this one are. So just to get a visual of what these functions look like. Okay, so in the rest of the talk, I'm first going to cover the lower bound. And then I'm going to make an assumption that's somewhat strong and show you a matching upper bound. And finally, we're going to get rid of that assumption and get an almost matching upper bound. And so to cut to the punchline a little bit, we're going to get an order square root k lower bound, order square root k upper bound with the assumption, and order square root k log k once we relax that assumption. Okay, so here's the lower bound instance. And in this case, we have one arm, the blue arm, that's increasing for all time. And we have k minus 1 copies of the orange arm, which increases for the first t over square root k time steps and then flattens out. We choose which arm, which index gets the blue arm randomly. And it's pretty straightforward to see that the optimal reward is at least t over 2. And the reward of any algorithm is at most 3 times opt over square root k. And so you can kind of see this from the fact that an algorithm would get to play about at most square root k arms. And so there's like a 1 in square root k chance of finding the optimal arm. This is formalized more in the paper. And if they do find the optimal arm, they get at most optimal reward. But if they don't, they get this t over square root k. And so we have a randomized instance, deterministic algorithm. We use Yao's principle. And we can show a lower bound for randomized algorithms on a deterministic instance of order of square root k. So now for the upper bound, let's assume we know that the maximum value of the best arm, which I'm going to call f star of t. And so with this, the strategy is actually pretty straightforward. We're going to choose a random arm, keep playing it until we can no longer hope to get f star of t reward eventually. So let's work through a quick example. We start off pulling the arm projecting what we see forward, and the red line at 10 is f star of capital T. And the projection crosses the line, we're fine. We pull the arm again, still crosses the line, still happy, keep doing this. And things are good until they're not, at which point we stop pulling the arm. So the question is, how much do we get from an arm that we play for TI time steps? So we know that if we played an arm for TI time steps, at time TI minus 1, this projection forward was still at least reaching m when you project forward to time capital T. And so we can just use similar triangles computation to get the height of this triangle and use that to compute the area under the, the accrued reward. And we can write this as a function of the optimal reward because the optimal reward is a function of this parameter m. So that's good. And now we can use that to analyze the total amount of reward that the algorithm gets. And to do that, we're going to exploit some recursive structure in the algorithm. So this repeat block that I've boxed is doing the same thing over and over, but with one fewer arm and TI fewer time steps each time. So we can define a recurrence v of t prime k prime, which is related to the expected reward when playing the game with t prime time steps and k prime arms. I say related to because, again, there are some subtleties which are addressed in the paper, but you can think of it as this expected reward for now. So with probability 1 over k prime, we find the optimal arm, we get the optimal reward, and we're happy. With probability 1 minus 1 over k prime, we play an arm for t plus 1 time steps and get this reward that we calculated a couple of slides ago. And then we add to that the expected reward for the rest of the game. And we don't know which bandit arm we're going to choose and therefore what t is going to be, but it turns out to be sufficient to just take the worst case over the arms. And so we can apply induction and show that this is at least the optimal divided by order square root k. And so this gives us the matching upper bound when we have this assumption of order square root k. So finally, we should get rid of this assumption because in practice we might not have access to f star of t. And so in order to do this, we're going to estimate the parameter, and like any good bandits person, we're going to do it by exploring for t over 2 steps. And how are we going to do this? We're just going to take every single arm, play it for t over 2k time. And this allows us to extrapolate upper and lower bounds for where the arm is going to end up. From there, we can choose L and U such that f star of t lies in the interval LU, and U over L is order k. We can divide this interval LU into subintervals of doubling length. And so we know that f star of t lies in one of these subintervals. So when we choose an endpoint, one of these endpoints randomly, we get that with probability 1 over order log k, we've chosen the endpoint for the interval in which f star of t lies, which means that we've found a value that's within a constant factor of f star of t. So with a good guess, we get the same reward. And so the expected reward is, the competitive ratio you get from the expected reward is at most order square root k log k. So if you want to kind of squint at this talk and take away some life advice, which I don't necessarily recommend you do, but I did, try everything for a bit, make a good guess about what you can achieve, and then only work on things that will get you there. But this is a theory talk, and really the conclusion is just that the competitive ratio for this problem is between square root k and square root k log k. Thanks, and I'll answer any questions.
Thank you very much for this. This is super interesting. I've never seen this setting before. Oh, well, I've seen it in practice, but not in theory. Are there assumptions that can be made that can actually get you sort of no regret, sublinear regret, or even with, I don't know, Bayesian assumptions, is this hopeless? So is there like a solvable in the sense of, yeah.
Yeah, that's a good question. And to be honest with you, I don't know the answer to that. This is sort of the first Bandits problem I've worked on, and so like I am not very familiar with a lot of the literature. But if you have ideas, I'd be very curious to talk about them.
Are there more questions?
So for real life applications, it might be interesting to consider the case where the arms are not fully independent. Mm-hmm. Any ideas?
Well, so here the arms don't have to be, we don't make any assumptions on the arms except that they're increasing and that they have this concavity or this like diminishing returns property. So the adversary or the world could set them in a dependent way.
So the function regarding the reward would be independent of the other ones?
Mm-hmm. Or yeah, it could be
Independent or independent?
It could be anything. There aren't any assumptions on any structure between the arms.
Okay.
Thank you. I guess I may be mistaken, but like some people call this rising bandits. Have you heard of this terminology? Is it different?
So I think I think people do have. I think there is also like a line of work on the rising bandits question. My understanding is that there's like an asymptotic regret that's studied, which I think again is like you can't get a non-trivial one here, and then I think there's like randomness, like stochasticity.
Oh, yeah, maybe.
Yeah.
Perhaps, yeah, I'll check. Any other question? Okay, well then, in the interest of time, thank you again.